Hi, welcome to another hands-on demo for GEOEL221. This time I'll be working through the solution to a three-point problem. In this example, we have the base of the lower greensand unit measured at different elevations in three different boreholes. In the Worlington borehole, the unit intersects the borehole at minus 60 meters below sea level. At the Kentford borehole, the unit intersects at minus 75 meters below sea level. And at the Culford borehole, the unit intersects at minus 150 meters below sea level. We have a scale bar given here of 0 to 500 meters. And so the first step to finding the strike and dip of the lower greensand unit, based on this information, is to measure the strike line, or structural contour. So I'm going to use an onion skin piece of paper to overlay onto the map, just to help keep the map clean. I'm going to add some registration marks. So if the onion skin moves, I'll be able to realign it. And I'm going to transfer the locations of each borehole. We also have the scale bar here from 0 to 500 meters. And if we use a ruler to measure how long the scale bar is, it's about 4.1 centimeters for 500 meters. And this scale will apply to both the horizontal map and the vertical miniature trig sections we deal with to look vertically into the ground. Okay, so now that we have our scale determined, we connect our three boreholes with a triangle. Once we've connected our boreholes, the next step is to locate our highest elevation, which is the Worlington borehole at minus 60 meters, and the borehole with the lowest elevation, which is the Culford borehole at minus 150 meters. So to determine the strike line, we know that somewhere along this line, the elevation of the lower greensand formation will be 75 meters, which is equal to the depth at which the unit intersects the Kentford borehole at minus 75 meters over here. So to do that, we extend a section line perpendicular from this triangle using our Douglas protractor as a handy tool. So we line up the triangle line and with a straight line as part of the Douglas, and then we use the edge of the Douglas protractor, which is perpendicular, to extend up a section. All right, so now we have the beginnings of our section line, and just to give a bit of distance from the map for cleanliness, I'll transfer this line a little bit further up the page. This is an optional step, just for helping with clarity of your drafting. So if we take this line as the base of our section, we can set that elevation equal to minus 150 meters as the lowest point, and over here again is minus 150 meters. We want to extend our scale up this section at the same scale as what's given for the horizontal map. So we have 0.82 centimeters equals 100 meters. So if we use our ruler here, where we go from 0 and we go up 0.82 centimeters, which would be minus 50 meters. We have to then interpolate on this scale to find minus 60 meters. So we can say 0.41 centimeters is minus 100 meters. And some further interpolation to find minus 60 will be less than a millimeter. And we can call that our minus 60 meters. Once we have that 60 meters here, we know that the topography extends from this point to that point between minus 60 to minus 150. So we do that, we draw that connection on our little cross section with a straight line. All right, so there's that section line, and now we want to find at minus 75 meters where that line intersects. So again, we can return to our vertical scale bar here. Minus 75 meters will be around 0.2 centimeters. And either we can transfer that minus 75 meters to the other side of the axis with a ruler, or we can use our Douglas protractor here by lining up the perpendicular line so it's parallel to the edge of the Douglas protractor, and simply draw that line across. So over here, that's minus 75 meters. And now if I just move this onion skin off of that map a bit, it's easier to see where the descending elevation of the geological unit intersects minus 75 meter elevation is right around here. So now we transfer point X back to our original triangle, making sure the extension line is perpendicular to that side of the triangle. I'll reposition the onion skin on the map here. So now we have the point X on the triangle between minus 60 and minus 150 boreholes. That equals minus 75 meters. And we have all the information we need now to simply draw the strike line between these 2 points across the triangle. So the minus 75 that we've calculated intersects the minus 75 in the borehole down here. And this is our strike line. So we know north is parallel to the edge of the map, so we can use our Douglas protractor. So we can use our Douglas protractor to measure the angle from north as azimuth, so 1021 degrees. So that's our strike line here, or also known as a structural contour, at 21 degrees. Now the next step we want to find is what is the dip of this lower greensand unit. We solve that by using our strike line and the third borehole, which is the lowest elevation of that unit. So we have the minus 75 meter strike line as our intermediate elevation, and we have minus 150. So if we draw the same strike line of 21 degrees at our minus 150 meter borehole, again I'm centering the Douglas protractor on the borehole, and I'm using other lines on the map, such as the north arrow and the edge of the map, to make sure that the north of the Douglas protractor is parallel to the north of the map. So once we have that center point and we have our strike line, we make a construction mark at 21 degrees strike. Then we reposition our Douglas protractor and connect the 2 points. So this is the structural contour at minus 150 meters. Once we have these two strike lines drawn, and we know the depth of the unit along each strike line, we move on to the third step of the triple point problem to figure out what the dip is. So we make another sort of mini cross section here by drawing it perpendicular to the two strike lines. We know the intermediate elevation on this side is higher than the elevation over here, so it's dipping toward generally east-southeast. So if we take this origin line of the cross-section as minus 75 meters, we know our scale, which stays the same. So we go from this at minus 75 meters, and we want to find out where along this scale minus 150 meters lies. So 0.82 centimeters is 100 meters. So there's the 0.82 centimeters, and minus 75 minus 100 meters is minus 175 meters. Now we're interpolating between these 2 points to find minus 150. So half of that, 0.41 centimeters, is minus 125 meters. And if we take the halfway point between those two, about 0.2 centimeters, we have our minus 150 meters. So this is the point that we then connect across our section line. Like that. I'm just going to draw this line a bit longer because I'm going to be using that to measure dip, and I want this line to extend to the edge of the Douglas protractor. So now this angle here is the dip, and to find that we simply measure it. We know we're using a vertical scale equals horizontal scale, so the angle will be equivalent to what we measure with the Douglas protractor. So here we have our strike line, that 0 degree dip, and then we count down from there. So it's about 4 degrees. And there we go. That is our dip. If we're also interested in the dip direction, which is another convention that people use to measure azimuth, so it's similar to strike. The dip direction is the right-hand rule from strike plus 90 degrees, because the dip direction is the azimuth orientation of how the plane is dipping in space. So we know our strike is 21 degrees. We can simply add 90 degrees to that. Which equals 111 degrees. Or we can determine the dip direction graphically. We have the strike line and we have this perpendicular section line to strike, which is in fact pointing in the direction of dip. And we can measure that again with our protractor, making sure our onion skin is lined up on the map correctly. So if we have north, matching north on the map, and we count around the azimuth of our Douglas protractor to the line of dip direction, we read off that it is 111 degrees, which equals our calculation of simply adding 90 degrees to strike. So there we go. There is a full solution to the triple point problem. I hope you found this to be a helpful demonstration, and thanks for watching. Bye.